welcome back. So we are discussing, we saw last time that how qx square, rx squared, rx mod, x squared plus 1, this was isomorphic to C. So let us sort of repeat this construction because it will be useful to us in a slightly different context. So we have, you consider the set q root 2 equal to a plus b root 2, and a, b are rational numbers. Okay, and we are both rational numbers. This is inside R or C. And with respect to usual addition and multiplication of real numbers or complex number, this will form a ring. So if you have a plus b root 2, and if you add like a plus b root 2, and then if you add c plus d root 2, where a, b, c, d are in Z, right? Then you get, this is again of the form e plus f root 2, where e, f are in Z, right? If you multiply them, because BD into 2 and AC you can club together, and AD plus BC will be your F. Similarly, of course, A plus B root 2 plus C plus D root 2 is again of the form A plus C plus B plus D root 2. And A plus C and B plus D are integer. So clearly this set forms a ring. And and in this set, what is the additive identity? 0 plus 0 root 2 is the additive identity, and so 0 plus 0 root 2 is the additive identity, and 1 plus 0 root 2 is the multiplicative identity. So this clearly forms a ring. Okay, so that's what it's written here, that this is a commutative ring with 1 with respect to the usual. So this is the usual complex addition and multiplication. Further, if you have, is it a field? The question is. So you take 1 by a plus b root 2, where a plus b root 2 is not equal to 0, and a, b are in Z, so an element, non-zero element of this ring, right? Not the additive identity, which is 0. Then what is 1 by a plus b root 2? In the complex number, that is the inverse. So this is inside the complex number. So if this is a subring, then this inverse would be equal to actually what you calculate in the complex number, right? So in the complex number, the inverse is, or real number, the inverse is this. You multiply just by a minus b root 2 in the denominator and numerator, and you clear out the fraction part. So you write it again of the form. So this is again of the form. So you call this equal to E, right? This is E, and this is equal to F. So this belongs to Z, and this belongs to Z, right? So both these parts, if you like, this part, sorry, I said Z, I mean Q. This belongs to Q, and this also belongs to Q, right? So it is of the form, again, of the form A plus C plus D root 2. So that means this is a field. So Q root 2 is a field. Further, as I said, I'll mimic the construction from Qx to Q root 2. You have this map, x going to root 2. Fx goes to f of root 2. Right, like there we had sent the map x going to I, or fx going to f of I. So if you have a polynomial, and this is a polynomial ring in one variable, and if you have a0 plus a1x plus a2x squared plus anx to the power n, you send it to a0 plus a1 into root 2 plus a2 into root 2 squared, which is 2, plus an into root 2 to the power n. These ai's are in Q, right? So this is the map phi. This is the map phi, right? So, so fx goes to, simply if we put x equal to root 2 in the polynomial fx, right? That's what this is doing. Fx goes to f of root 2. So this is a clearly ring homomorphism. You can check again. And what is the kernel? So kernel x. So if x goes to root 2, then x square. Sorry. So then x square goes to 2 or x square minus 2 goes to 0. So you look at any multiple of x square minus 2, that will go to 0. And so x square minus 2 is contained inside the kernel. So the kernel contains the ideal generated by x square minus 2. And this homomorphism is also surjective because a plus b root 2 is captured by a plus bx, right, under phi. So this is surjective. So that's why this map is surjective. And you see, it's easy to check if if you go to the Rx, then if any polynomial goes to 0, right, under this map phi, then root 2 will be root of that polynomial. So, and this because it is defined over rational number, you can check minus root 2 will also be a root of it, and then you can check that x square minus 2 will be a root of it. So kernel will be exactly equal to this. So it's not difficult to check. Okay, so then you get qx by x square minus 2 by the isomorphism theorem we proved. You have a surjective homomorphism phi, and the kernel contains x square minus 2, and kernel is exactly equal to x square minus 2. This map is surjective. So by the first isomorphism theorem brings q root 2, this field is isomorphic to qx by x square minus 2. So how did you obtain this? So we have this polynomial ring and you quotiented it by some ideal, and then you got a field, and this field is isomorphic to q root 2. Further, we know q root 2 contains q, right? So q is contained inside q root 2. So it's a subfield of this. Even if you look at qx by x square minus 2, you have a map from q to qx by x square minus 2. So what is the map? Map is you send any element a to the constant polynomial, right? So to the quotient, so you send it to a going to a plus I, where I is x square minus 2, right? This a going to a, sorry, a going to a plus I, where I is x square plus 2, right? A is a constant polynomial. So I can send this map and you can check clearly this is a ring homomorphism, right? From this field Q to this ring Qx mod x square plus 2, and which is x square minus 2, which we have seen is a field, right? So this is a field homomorphism, and what kind of field homomorphism it is? See, one is going to 1 plus x square minus 2, this, and 1 plus x square minus 2 is not equal to 0, because if 1 plus x square minus 2 would be equal to x square minus 2, this ideal, then that will imply that 1 belongs to x square minus 2, this ideal generated by x square minus 2, and this is the principal ideal, that will mean 1 equal to fx into some x square minus 2 for some fx belongs to qx. But then you can count the degree here is 0, degree equal to 0, and here degree is 2 plus degree of fx, right? So 2 plus degree of fx is equal to 0. That's not possible because degree of fx is not equal to 0. Okay, so that 1 is not in this ideal x square minus 2. So if 1 is not in x square minus 2, then 1 plus x square minus 2 is a non-zero ideal. So you gave a map which is a non-zero field ring homomorphism from a field which is non-zero, right? So you have a field Q, and from here you gave a ring homomorphism which is non-zero. So as we have discussed in the last class, that this field homomorphism is injective, right? Non-zero ring homomorphism from a field is injective, we have seen, right? So that means Q is contained inside this field, Qx by x squared minus 2 as well, right? So in fact, you can think in this way. We also introduced this notation sometime, writing x bar, quotient like x bar. So we can think of this polynomial, this is not a polynomial ring, but we can think of this a plus b x bar, where a and b are in Q. And x bar has the property that x bar square minus 2, x bar square equal to 2. This is the property. So whenever I see x bar square, then I'll put 2. So that means if you see that this is a vector space, Q vector space of dimension equal to 2 generated by 1 and x bar. So Q sits inside this field, Qx by x squared minus 2. And from your elementary linear algebra, you know whenever a field K is contained in a field F, then F is a K vector space. This is basic linear algebra, right? Think about it. If you have a field contains another field, uh, two fields, there is a containment. This bigger field is a vector space over the smaller field. So since Q is contained inside this Qx mod x square minus 2, then the Qx square minus x square minus 2 is a vector space. And I'm saying, what is the dimension of this vector space? Dimension of this vector space is nothing but 2, n by 1 and x bar. So these are the things we'll remember. So we constructed a field Q root 2. Now you can think about why this isomorphism. You can think we have constructed a field uh, where Qx, we attach the polynomial ring over Q, we have the polynomial ring and quotiented out by an ideal x square minus 2. And then we got this isomorphism Q root 2. This x square minus 2, if you think about it, is actually an irreducible polynomial. So we'll use that later. And then from Q, there is an injective homomorphism there. Just like on the right hand side, Q injects inside Q root 2. Here also there is an injective homomorphism. And and it's a vector space of dimension 2 over Q. So actually, what is x bar? X bar satisfies x bar square equal to 2. So x bar is in some sense nothing but root 2. So there's a canonical identification with, so you compare this a plus b root 2, a b is in Q, right? So here also a plus b x bar, we can write it, we can introduce in this notation all this element, because whenever you have x bar squared, you'll put 2, right? Because that's what you are quotienting by. In this I, if something is in I, it is 0. That means what happens in I? Something is in I, so I, the main property is x bar square equal to 2. So you can identify this, and so a plus b x bar is nothing but there's a canonical identification via your phi with a plus b x bar, where x bar is some sense root 2 a plus b root. Okay, so this is, so one calls, so if it's a vector space of dimension, one says that qx mod x square minus 2 is a field extension of degree equal to 2 over q. Okay, and you see what is this? This is equal to q root 2 means what? See, here we have this identification. What is this identification with? Again, if you look at it. So what is root 2? Root 2 is the root of this polynomial. So you have taken qx, and this is an irreducible polynomial. You have quotiented out with this irreducible polynomial. You got it a field over q, which in some sense is generated by this. The field is generated by this, the root of this irreducible polynomial. Okay, so we have a polynomial ring over Q, and we quotient it out by a reducible polynomial. Then it is identified with a field. It is generated by the root of this reducible polynomial. What is the meaning of generated by? It is precisely that every element here is of the form a plus b root 2, where a, b are in Q. So it is generated by over Q, just one element root 2 generates this. So we'll come back to this. This will be a theme which we'll discuss later. Okay, so let us go back to ideal and prove some interesting theorem. So one is the operation of ideals. So let I and J be two ideals in a commutative ring with identity A, and then define the sum of those ideals. Okay, so if you have two ideals, we define various operations on the ideal. One is the sum of the ideal. So what is the sum? If you have two ideals I and J in a commutative ring A, as I said, all rings are commutative and all rings have identity in this course, so I may not repeat it all the time. So define I plus j is to be the set of all elements I. So set of all I plus j, where small I is in capital I and small j is in capital J. So you can clearly see that this is an ideal because this is an additive subgroup, and it has the identity element 0 plus 0, and inverse of an element I plus j is minus I plus j, and so on. And if you multiply by any element in R, R times I plus j is, so if you like R times I plus j for R is in A, then it is Ri plus Rj, but Ri is in I1 and Rj is equal to J2 or J1. So it is I1 plus J1. So it is again in I plus J, right? So it clearly forms an ideal. Now next is also you can see if I and J are two ideals, then I plus J is also an ideal. Sorry, I intersection J is also an ideal. Uh, that's also not difficult to see. So if X is in I intersection J and Y is in I intersection J, then X plus Y will be in I intersection J. And if X is in I intersection J and R is in A, then R times I will be in I intersection J, and so on. So this is an ideal. And further, if you define next third operation is product. So if you define Ij, uh, so product is defined in a slightly different way. So if you just define I times j, where I is in I and j is in j, then immediately what you can see, this is not an additive subgroup. Hmm. So if you take I1 J1 plus I2 J2, they may not look like. See, if you take I1 J1, so I1 J1 plus I2 J2, there is no reason why it will be of the form I3 into J3. So that's why this is not an additive subgroup in general. So product of an ideal is defined as all possible sum, finite sum. So n in n varies. So you take a in I and b in j, and you consider a times b, but you take finite sum, all possible finite sum of this time. So a1 b1 plus a2 b2 plus a n bn, where ai's are in I, bi's are in j, and n in n varies. Okay. So all possible finite sum of product of elements from I and J. And why did I do that? Because to make it the first condition of an ideal is abelian subgroup. If you just take on the nose that I times J, then it is not an abelian subgroup. So you first make it an abelian subgroup, and now you can check that all the properties will be satisfied. But notice another thing. So this is so check that I times J is an ideal. Notice one thing here, that each element a is in I and b is in j. So in particular, b is in I. So this ai times bi is in I. Similarly, bi is in j and ai is in I. So this a times b is also in j. So they are in I and they are in j. So they are in I intersection j. Each of this. Okay. So so their finite sum is also contained in I intersection j. So the product is actually smaller than so product is actually contained in I intersection j by definition of ideals. Okay. So this is one thing to notice. Next concept is co-prime ideals. So two ideals. So if I and j are two ideals. So suppose you have two ideals, I and j, in a commutative ring A, are said to be co-maximal or co-prime. Excuse me. Or co-prime. Both the terminologies are used. Ideals if, so if I plus j is equal to the whole ring. Okay, if I plus j equal to the whole ring, the whole ideal, then you call them to be the to be co-maximal ideals. Okay, so further co-maximal or co-prime ideals. So for example, if you have 2z and 3z, then this is equal to whole of z. So this happens if and only if, so A I have written ideal generated by 1. So I plus j, so example. Uh, so I plus j equal to A implies there exists I in I and j in j such that I plus small j equal to 1, right? So if I plus j equal to whole of A, then in particular A has the element 1. So 1 can be written as 1 is also an element of I plus j. So how does an element of I plus j look like? It's an element of I plus an element of j. So there exists I in I and j in j such that I plus j equal to so example. And more generally, just excuse me. Okay, more generally, if I1, I2, In are finitely many ideals in a commutative ring A, they are said to be pairwise co-maximal if their sum is equal to the whole ring. Okay, so if I give three ideals like I1, I2, I3, then you call them pairwise co-maximal or pairwise co-prime, co-maximal or co-prime. Okay, if you take any two distinct I plus Ij, then their sum is equal to E. Then you call them pairwise co-maximal. Okay. Okay, so observe that if I plus j equal to okay, so it's just the generalization of the two ideals are said to be co-maximal if their sum is the whole ring, and if you have a bunch of them, then are called co-maximal. If you pick any two of them, or co-prime, if you took any two of them, then their sum is equal to the whole ring. So that's what I said just now. So if I plus j equal to the whole ring, then there is I in I and j in A, such that I plus j equal to 1. So now, if that happens, as I explained, so if I plus j equal to the whole ring, then there is I in I and small I in capital I and small j in capital J, such that I plus j equal to 1. This implies if y is in I intersection j, then y can be written as, now you take under this condition, if y is in I intersection j, then y can be written as 1 times y, which is I plus j into y. So I times y plus j into y, right? Because 1 equal to small I plus small j. So y I can write any y. So for any y in I intersection j, y can be written as y equal to 1 times y. So 1 equal to this I plus j for these two particular elements. So it is I times y plus j times y. But I times y, I is in I and y is in j. So because y is in I intersection j, so I times y belongs to ij. Similarly, j is in j and y is in I. So this belongs to j times I, which is I times j because ring is commutative. So this is also in ij. So their product, their sum is also in ij because it's an ideal, right? So all possible finite sums are there. So that means this element y is in ij. So I intersection j is contained in ij. I intersection j is contained in ij. And we saw ij is always, by definition, is contained in I intersection j. So we get that I intersection j equal to ij. So this is a special case for co-maximal ideal. So until this was a general observation. We defined some product and intersection, of course, of ideals, and all of them are ideals with the appropriate definition. Then the way we have defined product, it is contained in I intersection j. But if in a special case, if the I and J are co-prime or co-maximal ideal, then both the terminologies are used in some books. So I said both in case you read some book. So then I plus J is equal to A. Then I intersection J is actually equal to IJ. Okay, and the one last concept we need before you introduce this theorem, which is that product of rings. So we have defined product of groups, direct sum of groups. Similarly, if A1 and A2 are two commutative rings, okay, two commutative rings, then their product is the Cartesian product, all xy, where x is in A1 and y is in A2. It's simply the set Cartesian product. And the addition and multiplication is defined component wise. So if you have x plus y plus a plus b, then it is x plus a and y plus b, where a has the operation, let's say, plus 1, the first string has operation plus 1, and multiplication cross 1, and second ring has operation plus 2 and multiplication cross 2. Then x plus y will be x plus 1a, and y, the operation of a2, you define addition. You add y and b in the operation of the second ring, and similarly xy times ab will be x times a, where this in the operation of the first ring, and y comma y times b, where this is in the operation of the second ring. And 0 and 0 of a1 and a2 respectively with the identity, and the tuple 1 comma 1, the ordered pair 1 a1 and 1 a2 will be the multiplicative identity. So clearly this forms a ring, and I have denoted it by a1 cross a2, and just the notation consistency, like for abelian group of a, so a1 cross a2 was earlier denoted by a1 direct sum a2, but that doesn't matter. The definition is exactly the same. I'm using two notation because generally for abelian group, this notation is used. Generally for rings, this notation is used, and there is some reason for it. If you extend it to infinite, only many ring or abelian group, these two things could be different. So, but anyway, so when you see, so if you see in particular, if I set this notation, then by our notation, just for convenience, Z mod mz, for example, cross Z mod mz. This is same as Z mod mz, the notation, direct sum Z mod mz. So if you see this. So don't get confused. Different books uses different notations. So as abelian groups. Okay, so abelian groups. Abelian groups. Okay, so for all practical purposes, you can remember this. Okay. So so now with this, we can state an important theorem, which will be important for us. If I1, I2, In are pairwise so if I1, I2, so I talked about define what is coprime and co-maximal ideals. So if I1, I2, In are pairwise coprime or co-maximal ideals in a commutative ring A, coprime and co-maximal are the same thing, two different words. Then A quotiented out. So you can take, so you define product of two ideals. So similarly, you can define product of n ideals. And this quotient is same as, so this is an ideal, this is a commutative ring. So you can take the quotient ring. This quotient ring is actually equal to isomorphic to, so you take I1 intersection I2 intersection In. Okay, intersection of these ideals. This is an ideal. So A is a commutative ring. Again, you can take the quotient. So these two quotients are isomorphic, and further they're isomorphic to A cross I1 cross A cross I2 cross A cross In. So you have n rings. You can define their product in the similar way. I1 is an ideal in A, so you can define A cross I1. I2 is an ideal in A, so you can define the ring A mod I2. A quotient ring I1, A quotient ring I2. You can take their product. So this is a ring, and similarly A mod In we can consider, and inductively we can define, or we can directly define as n tuples and component-wise addition and multiplication. We can define product of rings. So all these rings are isomorphic. And not only these are isomorphic via the natural map. What is the natural map? So you look at the second one, or this one, x goes to x plus I1, x plus I2, x plus In. Via this map, it is isomorphic. So we are specifying this map. Natural is, some sense, the natural map phi, which sends x to the x bar or equivalence class of x plus the coset x plus I1, x plus I2, x plus In. This map gives an isomorphism. So proof is by induction. First we will prove for n equal to 2, and then we will do the general case. Okay. So n equal to 2 case, so suppose there are two ideals I1 and I2, then A mod I1 times I2 is isomorphic to A mod I1 intersection I2 is isomorphic to A mod I1 plus A mod I2 via the map x goes to x plus I1, x goes to x plus I2. That's what this is saying. So actually, the first one is actually an equality, as you will see that you have I1 intersection I2, I1 times I2, because they are pairwise co-prime or co-maximal, right? We just saw that if two ideals are pairwise co-prime, then their intersection, their product I1 times I2 is equal to I1 intersection I2. So A mod I1, into I2 is actually equal to A mod I1 intersection I2. This we just saw. And now you define a map phi from A to A mod I1 cross A mod I2, sending x to x plus I1, x plus I2. This is the map we have specified that under this map we want this to be isomorphism. So first two part is, so this part equal to this part is okay for n equal to 2. And this is clearly a ring homomorphism. You can check this trivial, it's a ring homomorphism. And what is the kernel? Kernel will be those such that x plus I1 equal to 0 and x plus I2 equal to 0. So what is the meaning of 0 in this quotient ring? X plus I1 will be equal to I1 and x plus I2 will be equal to I2. So x plus I1 is I1 means x belongs to I1. And x plus I2 is I2 means x belongs to I2. So x belongs to I1 and x belongs to I2. So x belongs to I1 intersection I2. So if something is in kernel, then it is in I1 intersection I2. So you can say this kernel is contained inside this. But if something is in I1 intersection I2, then x plus I1 will be equal to I1 and x plus I2 will be equal to I2. So this will be a zero element here. This will be a zero element here. So kernel is exactly equal to this. Okay. So kernel is exactly equal to this. And now the main important thing is to prove surjectivity, because it seems like we are giving a diagonal map, right? X goes to x comma x in some sense, but you want to capture all AB. So take any A plus I1 and B plus I2 in this ring A by mod I1 cross A mod I2, and we are saying that this will be coming from a single x. You have to produce a single x in A such that x plus I1 will be equal to A plus I1 and x plus I2 will be equal to B plus I2. Single x. So only thing we have in our disposal that I1 and I2 are co-maximal ideals. So I1 plus I2 equal to whole ring. So there exists I1 in I1 and I2, small I2 in I2, right? Such that I1 plus I2 equal to 1. This is the definition of co-maximal ring, right? So then you define, so you do this crisscross. So you are given two element A and B and you want to capture them. So A times you take I2 and B times you take I1, right? So and define AI2 plus BI1. Okay, so you define AI2 plus BI1. Then what happens? Y plus I1. So you define this to be equal to Y. Okay, I was calling it X. So this is the definition. Y to be equal to this. Then you look at what happens Y plus I1. So it's a small trick. So you wanted to capture AB. So you took A times I2 and B times I1, where I1 plus I2 equal to 1. Small I1 plus I2 equal to 1. And this came from the definition of co-maximality. Then Y plus I1 plus Y plus I2, what it is? It is AI2 plus BI1 plus I1 and AI2 plus BI1 plus I2. Sorry, here. So this stage we have not done anything, we just applied the definition. Y goes to Y plus I1, Y plus I2. This is equal to Y. So there is nothing here. But since I1 is in, now notice that since I1 is in capital I1, small I1. So B times small I1, this is also in capital I1. So this is an element of I1 and this is I1. So this coset is nothing but AI2 plus I1. Similarly, you see Similarly, I2, small I2 is in capital I2 and A is in the ring. So A times I2 is in capital I2. So AI2 times capital I2 plus capital I2, this quotient is nothing but I2. So I can write it as I2. So I'm left with here AI2 plus I1 and BI1 plus I2. But I2, I can again write 1 minus I1. So this is nothing but A minus AI1 plus I1. And similarly, here I can write B minus BI2. I1 I can write 1 minus I2. So B minus BI2 plus I2. But again, I1 is in capital I1 and minus A is in the ring. So minus AI1 is in capital I1. So this is nothing but I1. And similarly, small I2 is in capital I2 and minus B is in the ring. So minus B times I2 is in capital I2. So minus BI2 plus capital I2 is not equal to I2. So I got A plus I1 and B plus I2, right? This becomes A plus I1 and this becomes B plus I2. So thus is so this is equal to A plus I1 and this B plus I2. So this is what you wanted. You started with A plus I1 and B plus I2, and you captured it by single element in the ring A, which is Y plus I1, and Y. It is of the form Y plus I1 plus Y plus I2. So phi is surjective, and we get a ring of isomorphism phi A mod I1 intersection I2 is A mod I1 cross A mod I2. So n equal to 2 cases, done. So in the next class, we'll complete the proof and we'll see the uh, general case. Okay, thank you, and we'll meet again.